Okay, so here it says the quantum frequency associated with dominant pole is roughly omega 0, and f0 is 1 Hz. This is because here at 1 Hz we approximate have our bandwidth here. Effects of sampling. So sampling process will produce a time delay. So this is the OH, and this is our original signal. So you see there is a time delay here, which is T/2 here. So UT is input of UT is a continuous signal, and the UKT is a discrete signal. So the phase is T/2 compared to original signal, and at a frequency of omega, this will corresponds to a phase lag of omega t divided by 2. Phase lag increases with higher frequency, and according to Nyquist sampling theorem, this will lead to, because TSF equals 2 omega divided by 2 pi, it will be 2, give it like S. That's Nyquist sampling theorem. Choosing the sampling rate to be 30 times bandwidth, this is from our last video where we want to use the Euler approximation. So it will become 30 in front of omega divided 2 pi instead of 2. This will result in a much smaller phase lag of pi over 30, which means just 6 degrees. For PID controller, this is also concept from the control system, where it's briefly mentioned here. So for a proportional gain, which means P plus an integral gain I and a derivative D, a PID takes a form of D equals U divided by E equals K, and in bracket that's 1 plus 1 over TS and plus TDS. This needs to be memorized. Euler approximation, backwards difference, and we also have forward difference. This is to derive a discrete approximation to the continuous controller. We start by writing a differential equation. This means we expand it out of U and E and differentiate U to get rid of the integral term. So next, because where does the E come from is you times the E to the bracket on the right hand side, and you differentiate it. We need an approximation for the second derivatives as well as the first one. So we differentiate again for the E, so you will see this equation. This is because EK minus E minus K and minus the EK minus 1 minus EK minus 2. That is the second difference. Rearranging this will give the formula for UK. The coefficients of these are constant, so hence the recursion can be written in a standard form. So this is our standard form. So let's see an example. So consider a plant consisting of small servo motor with a transfer function, which is GS. I suppose the speed is measured by a sensor, 1 volt per radian second. So use K equals 5, TD equals 0.008, and TI, the continuous controller produces satisfactory response below. Compare this with second order step response. Okay, we come across this again for 168 page. That is our step response, which we introduced earlier. So we will compare this graph to find the approximate damping coefficient, which should be, what does it say? He didn't tell me the coefficient he chose. So anyways, let's continue. The natural frequency here is because this is roughly around here. Indicate a bandwidth around 200 Hz. Sample at 30 times the bandwidth will give a sample rate of 7.5 kHz. Step response at a sample rate of 10 Hz. So this picture shows a step response with a 10 kHz sample rate. This is an acceptable response. Because we said that sampling at 30 times larger, otherwise it will introduce a lag as well as not being very stable. It will oscillate. So the above somewhat attribute truth of sampling rate and ad hoc tuning may be good enough for a simple system. To eliminate the approximate errors, we need to consider how to analyze in detail. So in our summary, this section discusses the choice of a sample rate, which is 30 times. Where is it? It is 30 times. 30 times this bandwidth, and the bandwidth can be find from the graph. The continuous time controllers may be approximated in discrete by difference equation. And you remember we will find the difference equation and also the second derivative to use the difference equation, Euler approximation. With construct by a ZOH. What is the assumption? We mentioned this in our last video. Reconstruct by a ZOH will introduce a delay of t/2. This is an equivalent to the phase delay of omega t/2 at frequency omega. The phase delay implies a more oscillatory response, but the delay has negligible effect if the sample rate is greater than 30 times the bandwidth. Next comes to the Z transform. In continuous system, the Laplace transform is used to transfer differential equations to algebra ones, since the latter is easy to use. And Z transform is to transform difference and recursion equations to algebraic ones, and construct a discrete transfer function. The Z transform Ez of a discrete signal, which is E0, E1, E2, E3. So Ez will become the symbol of Z transforms the EKT. So KT we know that is a discrete signal. And to the Z transform means there is a sum sign and the Z to the minus K here. And the EKT, remember from the first video, it can be written as EK. A decaying exponential signal, where ut is a unit step function. To give xk equals this. Okay? So this is the t. And then xa, so that is the one after trade transform, will be used the standard equation where we can take the coefficient out and sub in the xk. And then so because we have found there are 2k here, so we take it out. Look at this equation. And this is a geometric series and has closed form if z is greater than e to the minus at. So this will become